All right, guys, so we're going to go ahead and start off, and we're going to cover some advanced packet walks. But before we do packet walks, we need to talk a little bit about address learning. That's going to allow us to properly understand packet walks in ACI. So the first thing we can talk about is regular address learning in a traditional network. So when I say traditional network, that could be like an iOS switch or an NXOS switch. And notice here we have a regular Nexus switch. There's a server attached to it. It has an IP address and MAC address. And if that server powers on for the first time, it sends its first frame or packet to the switch. The regular switch is just going to learn a MAC address. ACI is a little different. So let's say we take that same server and we attach it to Leaf 101, interface 11. It sends a packet. The Leaf switch, so that's its local Leaf switch, has the ability to learn MAC addresses, but also has the ability to learn IP addresses as well. So that's one, I would say, big key point in ACI is we can learn IP addresses, and there's some benefits to doing that, and we'll look at that a little bit later on. There's a couple other important points with endpoint learning. So we saw that Leaf 101 can learn the IP and MAC address, but it actually does something. It does something unique to ACI. When Leaf 101 learns that local server's IP and MAC address, what it will do is it's actually going to go tell the spine switches about the endpoint learn. So it actually uses a protocol called COOP, which stands for Council of Oracle Protocols. And essentially what it does is it tells the spines that it has a new endpoint. And so if we think of the big picture, what we're doing here is essentially all spine switches will know the location of endpoints attached to the ACI fabric. So in this example, spine 203 and spine 204 is going to know that IP 10.13.11 and MAC A are behind Leaf 101. So that's a very important concept to understand some of the packet walks that we're going to do. The other thing, so spine switches should know about all endpoints. Leaves won't necessarily know about all endpoints. It should know about locally attached endpoints. So Leaf 101 will know about that locally attached endpoint. It may not know about an endpoint referred to as a remote endpoint. That would be behind Leaf 102 in this example. Leaf 101 is only going to learn a remote endpoint if a device, a local device attached to it, has an active conversation with that remote endpoint. So for Leaf 101 to learn about that remote endpoint, notice these two devices are having an active conversation. So because of that, Leaf 101 has the ability to learn about that remote endpoint's IP address and MAC address. And Leaf 101, from its perspective, it's going to say, or in its table, it's going to say, hey, that IP address 10.13.12 and that MAC are behind Leaf 102. So that's another important concept as well. We'll talk in much more depth about COOP, that COOP protocol or Council of Oracle's protocol, and endpoint learning in a later topic. But for now, I just wanted to kind of get you familiar with endpoint learning because you have to understand a little bit about that to understand the path of the packet in ACI. So we're now going to do some packet walks. We're going to go through a couple different scenarios. So here's our ACI fabric. Notice here, in ACI created one VRF. I created one bridge domain. I created EPG1. And let's say we have one endpoint using that EPG. So we have endpoint 11, and you can think of that as just like a server. And then maybe we also created EPG number 2, and we have another endpoint in EPG2. That's referred to as endpoint 2 1. And again, you can just think of them as servers. So this scenario is pretty simple. What if these two endpoints want to communicate and they're attached to the same leaf? Well, the traffic is going to be locally switched or locally forwarded by the leaf switch. So if those two endpoints are in the same subnet, leaf 1 is just going to locally switch the traffic. If those two endpoints are in different subnets, in ACI, we typically will route or forward at the leaves. We have those SVIs that are running on each leaf switch, Anycast gateway. And so the leaf switch would locally route the traffic. So this is a very simple packet walk here. In the next packet walk, we're going to actually focus, what if we have two endpoints on different leaves and they want to communicate? So let's say those two endpoints, one's attached to leaf 1, the other's attached to leaf 2. They're in the same VRF. They're in the same bridge domain. We have EPG1, and right there attached to leaf 1 is endpoint 1.1 right here. And then we also have EPG3, and endpoint 3.1 that is attached behind leaf 2. So if these two endpoints want to communicate to each other, the traffic needs to be sent over the ACI fabric. So this is going to be a little bit more complex. We do some kind of fancy things when we send traffic over the ACI fabric. The one thing I want to talk about, so before we do this full packet walk where I show you how we send traffic over the ACI fabric, I want to talk about something called a TEP IP address. And so notice we have 5 switches in the fabric. They're all going to get assigned a unique IP address referred to as the TEP IP, also known as the tunnel endpoint IP. That's a VXLAN term. And they're each going to get their own unique IP. And you can see these IPs that have been assigned to the switches in the ACI fabric. You can also see it in the GUI as well. We'll go ahead and look at a command here. So I can run this from anywhere. I can run it from the switches or the APIC. I'm running the ACI diag fnv read command. And notice here that all the switches have a unique IP. And notice they all start with 11. So I have a question for you. And anytime I say I have a question for you, feel free to pause the video to think about it. Where do those IP addresses come from? Where does that range come from? So the answer is the TEP IP range comes from when you initially set up your APICs. One of the things you specify when you're going through the initial setup is the TEP IP range. You'll specify the allowed IP or the IP range that's going to be used for the TEP IPs. So big takeaway is every switch in the ACI fabric is going to have a unique IP address referred to as a TEP IP. So you'll see how this TEP IP gets used in our upcoming packet walk. All right, so we're going to go ahead and do a packet walk between endpoint 1.1. It's going to communicate to endpoint 3.1. That's behind leaf 2. Endpoint 1.1 is behind leaf 1. And so let's just say they're on the same subnet. And let's say that endpoint 1.1 sends a frame destined to 3.1. It's a unicast frame. And so if we look at the layer 2 header here, it's pretty simple. So the source MAC is going to be endpoint 1.1. Destination MAC will be endpoint 3.1's MAC. And the same thing for the IP. Source IP will be endpoint 1.1. Destination IP will be endpoint 3.1. So this frame is going to come into leaf 1. Leaf 1 is going to look at its table. Now, we talked about endpoint learning at the beginning of this lecture. Let's just say that leaf 1 knows that endpoint 3.1 is behind leaf 2. So let's say it knows where the destination is. So in this example, what it's going to do is it's going to send the traffic over the ACI fabric. And here's a key point. So anytime we send traffic over the ACI fabric, we need to add a VXLAN header to the original frame. So notice here, this is the original frame that I was talking about. we take that frame and we add an extra header on top of the original frame. So you can almost think of the original frame as being like insulated. It's being wrapped around an outer header. That outer header has a VXLAN header, an extra IP header. So this is referred to as the outer IP header, and then an outer MAC address as well. I'll talk a little bit about the VXLAN ID. So every VRF and every bridge domain created in ACI has its own VXLAN VNID. So since we're sending traffic on the same subnet, when we send it over the ACI fabric, the traffic's going to be sent over the bridge domain. So when you think of bridge domain, think of layer 2. When you think of a VRF, think of routing, layer 3. So the VXLAN ID would be the bridge domain VNID that will get inserted into the VXLAN header. And then for the source IP and the destination IP, that's going to be the IP, the TEP IP of leaf 1. The destination IP is going to be the TEP IP of leaf 2. And so what we're simply going to do now is we're going to route the traffic across the ACI fabric using that destination IP address, the IP address of leaf 2. The traffic is going to be routed over the ACI fabric to leaf 2. Leaf 2 is going to receive it. It's going to decap that outer header because it's destined for its IP. And what it's going to do is send the original frame down to endpoint 3.1. So endpoint 3.1 and endpoint 1.1, they just send and receive regular traffic. They don't have any concept that there's this outer header that's getting added to the frame when we send it over the ACI fabric. So it's kind of cool how that technology works. Now, in this example, we did a packet walk, or I covered a packet walk for the same subnet. If they are on different subnets, it pretty much works the same way. Obviously, what we're going to do is the destination MAC would be the gateway MAC instead. When endpoint 1.1 sends the traffic, it's going to be the MAC address of the gateway that resides on leaf 1. And when leaf 1 adds the outer header, everything's going to be the same except for the VXLAN ID. It's going to be the VRF VNID instead of the bridge domain VNID because we're sending traffic, we're routing traffic over the ACI fabric. All right, that's all I got.